Okay, we're back. All right, so we've talked about how to write rate equations, how to solve them, and we always did it looking at a change in concentration over a change in time. There are other variables that you can look at. For example, with gases, you might look at changes in volume or pressure. That's not something we do in a high school laboratory, so you will not be assessed on it in any regard. Also, one thing you'll see more in an advanced chemistry class is that the color of a solution can be used to determine the concentration of a solution, and that too is far too advanced. So in regard to this section, it's all very interesting, but it's nothing we're going to explore at this level, so don't be concerned. And what we really want to focus on now, and this all fits into our learning goal, are the factors that affect reaction rates. So we know that kinetics is the study of reaction rates and the factors that affect them. And now we're going to look at some of those factors. And if you think about some of the labs that we've done this year, even in the third lab we did in the first 9 weeks, we reacted zinc with hydrochloric acid, and we put the Erlenmeyer flask that held those two reagents on the hot plate. So we heated it, and we heated it to speed up the reaction rate. So temperature is one factor that affects reaction rate. We'll also be looking at the effect of concentration on reaction rate and the effect of altering surface area on the reaction rate. And in the lab next week, you'll be exploring how altering concentration affects the reaction rate by timing a reaction for it to change from clear to blue-black. Please don't play with your phones in here. You're not supposed to do that. Thank you. All right. With factors that affect the reaction rate, we need to understand the collision theory. And the collision theory helps to explain why concentration, temperature, and surface area can affect reaction rate. What we're looking at is that particles are moving around and they are going to collide with one another. An effective collision is one in which there's enough force between the particles and they're oriented properly such that you generate the products that you want. So when we think about, hi, okay, let's, I'll just take it here and I'll have the kids put it in. Is it heavy? Not sure. Don't run over my foot, please. Not that heavy. Thank you. Okay, so when we talk about the collision theory, the particles have to collide with enough force and they have to be oriented properly. So, anybody ever have a concussion? Okay. Who wants to go first?
Chloe from what?
Ladies first. I already am figuring somebody dropped her on her head.
Yeah.
But okay, so Chloe, what happened?
Well, which time?
Pick one.
I was flying and we were doing a pyramid and no one caught me and I landed like right on my head.
Right on your head.
Yeah.
So,
Like fell.
you hit the ground with a lot of force, right?
Yeah.
And your head was oriented such that it hit the ground probably first.
Yeah.
Yeah. So enough force and orientation of the head to the ground resulted in a concussion. This is why, for example, in football, they tell you not to lead with your helmet, because you know you're going to hit somebody hard, but you don't want to get knocked on the head too many times. They're finding a lot of football players nowadays have brain damage due to excessive numbers of concussions. And you see this a lot with boxers as well. A lot of people, when they retire later on, they're developing brain damage over the years because of concussions. Nick, how did you do it?
Turned to bunt and ball came right in my face.
Yeah.
And
So the ball hit you hard because somebody was probably pitching at what, 80, 90 miles an hour? 70?
It was a while back, so it probably would have been like 65, 70.
Okay. And your head, normally you would be, looking at the ball as it came in, but when you go to bunt, you square at the plate, and so the ball hit you where? So it caught you under you had a helmet on, didn't you?
Mm-hmm.
But
It caught me
still,
under.
it caught you under. Ouch. Did it break the skin?
A little bit.
Stitches?
No.
No. Then it's not too bad. All right. So that's what I figured. So enough force and proper orientation. And you can apply this to molecules as they react. Anything that increases the likelihood of an effective collision, one that has enough force and the molecules are oriented properly, is most likely going to affect the reaction rate. So for example, with concentration, let's say we moved all the desks over, we blindfolded everybody in here, and we ran around. An effective collision would be one in which you bumped shoulders. We'd get a few of them. Now if I invite 6 more classes in here, the number of effective collisions should increase greatly, increase in reaction rate. Temperature. As you increase the temperature, the particles move faster. The likelihood of an effective collision will increase in reaction rate. And we'll cover surface area, probably not next time, the time after that. So what you're looking at here is the decomposition of this substance to nitrogen dioxide and chlorine gas. So what you're looking at here are 2 particles colliding. They hit each other hard, but you want to generate chlorine gas. So this chlorine atom really has to hit on this one in order for a bond to form between them and break the bond that is holding these 2 together. So this is not an effective collision and no reaction occurs. You don't get your products. In contrast here, the chlorine atom hits up against this chlorine atom. A bond forms here. A bond breaks here. All we did was rotate the molecule 120 degrees so it would be oriented properly. This is going to be a successful collision, and now you get the 2 products as shown in the balanced chemical equation. So a successful collision is one in which you have enough force between the particles and they're oriented properly. So the first factor that we're going to look at is concentration. And whenever you're explaining why the concentration would likely increase the reaction rate, you always explain it through the collision theory. As you increase the concentration, the likelihood of effective collisions would increase in reaction rate. To understand how concentration affects reaction rate, chemists have derived rate laws, which we're going to look at now, the very simplest ones, and also we're going to look at reaction mechanisms, although I'll show it to you, it's not something you would be assessed on because it's really too complicated for the honors level, but certainly the rate laws is something we're going to explore, do quite a bit of work on, classwork, quiz, etc. So be careful though, a rate law is different than what we talked about initially. So with a rate expression, we had reactant and products, we had rates in there. With a rate law, you only have reactant concentration. That's all you're going to have is concentration of reactant, no product, and it's concentration, okay? A rate law is an expression for the reaction rate as a function of the concentration of one or more reactants. So for example, if this was your equation, 3 A's, so you've got reactant A being converted to product C. This is a rate law. Rate is equal to K. K is the proportionality constant. We're not going to solve for it. You're just going to put a K in there. Concentration of reactant A raised to the n power, where n is the order with respect to A. It will tell you how altering the concentration affects the rate, and we'll take a look at that mathematically. All right, so K is the proportionality constant, N is the order with respect to substance A, and you determine N from data, not from stoichiometric coefficients. You determine N from the data. Typically a small positive integer, it can be 0, 1, 2, 3, 4, 5, 6 maybe, but if you're getting higher than that, you've probably made an error. It can be negative, it can be non-integral, so it can be a fraction, but you won't see negative or non-integral at this level. You'll only see 0, 1, 2, 3, 4, 5, 6 at this level. So first we're going to look at how we interpret rate laws. This is very mathy, and then we're going to look at how we write them. And they're both very straightforward. You're going to be extremely good at this. It's very mathy, but you have to really think back to exponents. For example, what's 2 to the 0 power? 1. What's 2 to the first? 2. 2 to the second? 4. What's 3 to the second? 9. What's 3 to the fourth? No, 3 to the third is 27. 81, because it'd be 9 times 9. So it's just exponents. Just be very careful with your exponents. Let me show you how to interpret it. I'll show you how to write them, and then you can practice. It says how to interpret rate laws. So this is all written out for you, but I like to do it mathematically. So I'm going to correspond what I'm doing to A, B, and C here. It says when N is O, the order is 0 with respect to reactant A. So let's take a look at this. We're going to start with just the rate law we looked at previously. So for A, N is going to be 0. So the rate is equal to K, A to the 0 power. Or you could just say K, because A to the 0 power is 1. Anything to the 0 is 1. So let's say that the concentration of A doubles. So we have rate is equal to K, 2 to the 0 power is equal to 1 for this component here. So when you double the concentration, that's why we put a 2 in, the rate is unchanged. And it doesn't matter what we do to the concentration. If we half it, it's still 1. If we quadruple it and put a 4 in it, it's still 1. So it doesn't matter what you do to the concentration when the order with respect to A is 0. There's no effect on the reaction rate. Let's say that N is 1. The rate is equal to K, A to the first power. So now, if the concentration of A doubles, the rate is equal to K, 2 to the first power is 2. So the rate doubles. So here, whatever you do to the concentration, you do to the rate. Let's say the concentration of A quadruples. So I'm going to put a 4 in there now. That's 4. So the rate quadruples. So if it's first order, whatever you do to the concentration is what happens to the rate. So if you half the concentration, the rate is halved or decreases by a factor of 2, and we'll get into that in a little bit. Now, let's say you have second order, what would n be equal to? That's what I thought, it might not be clear. Okay, so if you have 0 order, then n is 0. If you have first order, then n is 1. So if you have second order, then n is 2. So rate is equal to k a. If you double the concentration of A, what's 2 squared? 4. So the rate quadruples. And if you quadruple the concentration of A, you'll put a 4 in here. What do you get? 4 squared is 16. So the rate increases by a factor of 16. I think I'm going to cut it here. I wanted to show you how to write them, but you look like you're done. And yeah, and I think with so many people missing, the next piece, I wanted to do a little bit today of it so that we could do all the hard stuff next time, but I just think it's too much. So I'm going to cut it there. I'll figure out what you can do on your classwork because it's a little less than what I thought. But we can spend the next 25 minutes just practicing, and there's still enough that you can do. If you finish early and you want me to show, then I'd be happy to show. So on your classwork, I told you about 1 and 2, and here so you can do 1 and 2. So it'll be 1 through 4 and 6. 1 through 4 and 6, and I'll hand that out now. And you can use the next 25 minutes to complete these problems. We'll go over how to write rate laws next time, and we'll get a lot of practice in. And your quiz will go through the rate laws, which are not hard. Is anybody posted? Oh, well, I wouldn't see you Friday anyway, so it doesn't matter.
Can you scoot up a little more?
Here?
In the corner, yeah, we can't sit at the corner. No, that other side.
So raise it up.
Here?
Factor of 16.
This is factor of.
A factor of 16. It's 16 times as fast. And we'll be doing much more of that next time too. Yeah, no, I know. It's tricky though. All right, so you guys did a great job as always. Now we have to figure